Welcome to AI Paper Slop. Today's paper is MoGe-3, which stands for Fine Detail Monocular Geometry Estimation with Self-Guided Sparse Volumetric Refinement.
Quite the mouthful, yeah.
Yeah, but here is the core insight you need to know right now. State-of-the-art monocular depth models, things like depth, anything 3 or, depth pro, they fundamentally fail at fine detail.
Right, like chain link fences or thin poles.
Exactly, the delicate edge of a chair, things like that. And they fail because they process 3D geometry using 2D image plane proximity. They basically squash the physical world flat.
Which causes the foreground and background features to just, bleed together across depth discontinuities.
Yeah. So MoGe-3 fixes this architectural mismatch by lifting the geometry from the 2D image plane into a 3D sparse voxel shell.
Right.
It uses the self-guided sparse 3D refiner, the SSR, to process features based on actual 3D spatial locality.
Which makes a massive difference.
Huge. The result is these extremely sharp, geometrically undistorted 3D metric point maps, and it runs at just 121 milliseconds with a VDITL backbone.
So it's beating existing models in both local fine detail accuracy and inference speed, which is wild.
Yeah, it really is.
And I just wanted to speak directly to you for a second, the ML engineer or, AI researcher listening right now. If you have ever wasted an entire Friday night frantically tuning DBSCAN clustering parameters.
Oh man, the worst.
Right. Just trying to salvage a 3D point cloud that was fundamentally broken by a 2D depth model, well, this deep dive is for you. We are going to explore exactly how MoGe-3 achieves this true 3D fidelity without requiring a supercomputer to process all that volumetric data.
So let's start with the root cause of those broken point clouds. The researchers behind this, they're from Tsinghua University, USTC, and Microsoft Research. They diagnosed this specific problem they call an architectural mismatch.
Yeah, it's a great term for it.
Because if you look at the landscape of monocular depth, you have feed-forward models using 2D convolutional decoders, right? And then you have diffusion-based approaches, like Marigold using VAE decoding.
Right, and even the recent methods adopting MLP heads over attached latents.
Yeah, exactly. But regardless of the specific mechanism, they're all trying to decode a complex 3D reality using a totally flat 2D grid.
Right, and the math of a 2D convolution introduces this inescapable local smoothness prior.
What do you mean by inescapable?
Well, think about a 3x3 kernel. It's a mathematical mandate to look at a pixel and merge its features with its immediate neighbors.
Oh, I see.
So if the center pixel represents a razor-thin foreground pole and the pixel immediately to its right represents, a building 100 meters away in the background, the network has no choice.
It just aggregates them.
Exactly. It aggregates those features. The architecture literally forces data from geometrically distant surfaces to just mix in the latent space.
So it's kind of like trying to untangle a massive pile of server rack cables by squashing them flat under a heavy piece of glass.
That's a great way to picture it.
Right, and then tracing them with a marker instead of just lifting them up in 3D space to see what crosses over what. 2D proximity is basically a liar when it comes to depth.
It is. It creates these visual illusions where things look adjacent on the sensor, but in reality they are separated by this massive void of empty space.
So that cable analogy, it really captures the mechanical failure of current foundation models. When 2D proximity diverges from true 3D relationships, local structural integrity just breaks down.
Yeah, the model oversmooths the geometry because the latent representation has fundamentally lost the concept of empty space.
Which is why fences look melted.
Exactly. Or why thin structures seem to stretch and smear into the background geometry. It's a structural failure.
Okay, so escaping the 2D plane seems like the obvious solution, right?
Right.
But that instantly creates a massive computational headache. If we abandon the 2D plane and try to process high-resolution geometry in full 3D, a dense voxel grid is going to require an astronomical amount of memory.
Oh yeah, cubing the resolution usually means your GPU just goes up in smoke.
Yeah, it's game over for VRAM. So how does MoGe-3 actually lift this computation into 3D practically?
Well, MoGe-3 avoids that dense volume trap by utilizing that self-guided sparse 3D refiner we mentioned, the SSR.
Okay.
The architecture relies on two main components, starting with a base model initialized for MoGe-2, which utilizes a DynaV2 encoder.
Got it.
And this base model acts as the foundation, generating an initial, slightly coarse 3D point map along with some foundational 2D feature maps.
Okay, so the base model gives us basically a rough draft of the geometry.
Exactly.
But how do we transition that into 3D without the memory explosion?
So the SSR takes that initial point map and performs what they call self-guided voxelization.
Self-guided.
Yeah. The genius here is recognizing that most of the 3D space in a scene is just empty air.
Right.
So instead of modeling a dense cube of voxels, it discretizes the point map into a sparse voxel set. The PAPE notes they factorize this mapping into image coordinates U and log depth.
Wait, yeah, I noticed that detail about log depth. Why quantize the depth axis, specifically in log space, rather than just using standard linear metric depth?
That is a crucial detail. Using log depth creates a scale invariant shell.
Okay, unpack that a bit.
Think of it like a logarithmic ruler. When you are measuring objects right in front of the camera, the hash marks on this ruler are packed incredibly tight.
So you get millimeter level precision up close.
Exactly. But as you look out to that building 100 meters away, the hash marks get wider. This perfectly matches how optical precision naturally degrades at a distance.
Oh, that's clever.
Yeah, and by multiplying this log depth by a specific resolution parameter, they use d equals 200 as their default, the voxel shell's density and connectivity remain mathematically consistent.
Regardless of the overall metric scale of the scene.
Right. You end up with this microscopic, thin manifold of occupied voxels that basically mirrors the 2D image resolution, but it's floating in 3D space.
I see. So every pixel in the 2D image maps to exactly one voxel in this sparse 3D shell.
Yeah.
But crucially, because it's now living in 3D space, that pixel of the foreground pole and the pixel of the background building are no longer sharing a border.
No, they're not. They map to voxels that are physically far apart along the depth axis.
Okay, so once those pixels are mapped to that sparse set, how do they process it?
That's where MoGe-3 deploys its Sparse 3D UNet. By using sparse 3D convolutions, the network only computes features on the occupied voxels.
So the empty space just costs nothing.
Exactly. The computation scales linearly with the number of points on the surface manifold, not cubically with the volume of the room.
That saves the GPU.
It does. But the most critical mechanical advantage happens during the downsampling phases of this 3D UNet, using a technique they call dynamic sparsity.
Okay, let's dig into the mechanics of that. Because in a standard UNet, when you downsample, you are essentially pooling a 2x2 grid of adjacent pixels together, right?
Right, to create a lower resolution feature map.
So how does dynamic sparsity work differently computationally?
Well, in a 2D UNet, that 2x2 pooling operation just blindly averages whatever happens to fall in that patch.
Right.
If a pole and a building share that patch, they get merged into a single lower resolution feature.
Right.
But in the dynamic sparse 3D UNet, the pooling operation tracks the exact 3D geometric coordinates.
Oh, wow.
Yeah. So if two structures collapse to the same XY image space location, but are separated by, say, 10 empty voxels along the z-axis, the sparse convolution mathematically skips the empty space.
Just refuses to pool them together.
It completely refuses. They remain isolated in the voxel grid, even at the coarsest resolutions deep in the network.
That's amazing.
It mathematically guarantees that foreground and background features never share a receptive field. It entirely prevents the feature mixing that plagues 2D networks.
So it predicts a log depth residual, like a tiny correction to the depth, and then it just loops this process.
Exactly. The default is 3 iterations. It predicts a correction, moves the voxels into their new positions, and then runs the 3D convolutions again on that newly refined spatial structure.
So that iterative structural update is the self-guided mechanism.
I got it. With each pass through the network, the spatial locality becomes more precise.
Meaning the convolutions in the next iteration are operating on even cleaner surface boundaries.
Exactly.
Okay, well, I need to push back on a specific architectural detail, though, because it seems completely contradictory to me.
Okay, well, let's hear it.
Looking at the network diagram, it shows them injecting 2D features, you know, those rich semantic appearance features extracted from the Dino-based model, directly back into the bottleneck of the 3D UNet.
Yes, it does.
But if we just went through all this incredible engineering effort to escape the 2D plane, specifically to avoid 2D feature mixing, doesn't injecting 2D features back into the bottleneck defeat the entire purpose?
It totally seems highly counterintuitive at first glance, I agree. But analyzing what a 3D voxel actually knows reveals why it's a brilliant design choice. A voxel in this sparse shell only possesses geometric coordinates. It knows where it exists in space relative to other voxels, but it has zero semantic understanding of the scene.
It doesn't know what it is.
Exactly. It doesn't know if it's modeling the leaves of a tree, a metallic car door, or a transparent pane of glass.
Right, so the 3D convolutions are essentially flying blind. I mean, they know the shape of the surface, but they have no idea what object they're actually refining.
They desperately need contextual priors. And injecting the Deno features maps those rich semantic understandings directly onto the voxels.
But how does it not mix them?
Because the mechanism of injection preserves the 3D separation.
Yeah.
If you have two voxels sharing the same line of sight, say one representing the foreground pole and one representing the background building, they both receive a duplicate of that 2D semantic feature.
Oh, I see.
But because the 3D convolutions are still strictly operating on the separated voxels in 3D space, they utilize that semantic context without blending the geometry.
Okay, that makes sense.
It gives the network vital information like knowing a sharp gradient is supposed to be there because it represents the edge of a building, without sacrificing the spatial isolation we just work so hard to achieve.
So it's essentially telling the network, here is what this ray of light looks like semantically, but forcing the 3D UNet to figure out exactly where along that ray the physical surfaces actually reside.
Exactly.
That is an incredibly elegant bridge between semantic understanding and geometric precision.
Combining semantic priors with strict geometric isolation is really the core innovation that makes this architecture function so well in practice.
But escaping the 2D plane solves the geometry problem, sure, but it creates a massive training headache.
Oh, absolutely.
I mean, if you drop a pristine, frozen 2D foundation model into a 3D pipeline, bolt an untrained sparse 3D UNet onto the end of it, and just turn on the gradients, it seems like a recipe for catastrophic forgetting.
It would be a disaster.
The chaotic gradients from the untrained refiner would just wreck the carefully tuned weights of the Deno base model, right?
Yeah, training instability is a huge risk with this kind of bolted-on architecture. So the researchers implemented a strict two-stage training schedule designed specifically to insulate the pre-trained base model from that initial chaos.
Okay, how does that work?
Stage 1 operates entirely as a warm-up phase. The base model's weights are frozen, and the gradients are completely detached. And even more importantly, the output layer of the 3D UNet is zero initialized.
Meaning it starts off acting as a perfect identity mapping.
Exactly.
It initially predicts a residual correction of exactly 0.
Right, and by forcing the network to act as an identity mapping out of the gate, the refiner is constrained to only learn residual corrections starting from a known good geometric baseline.
It prevents the 3D UNet from outputting wild random noise that would destabilize the learning process.
Yeah. And only after the 3D UNet is properly warmed up and making sensible minor geometric corrections do they move to stage 2.
Which unlocks the entire pipeline for end-to-end joint fine-tuning. The dataset curation for this training process is fascinating too, because they deliberately split the data based on what each part of the pipeline needs to learn.
Yeah, they were very careful about this.
The base model is trained on a massive mixture of synthetic and real-world data sets like A2D2, Waymo, Megadepth. Why is that variety so crucial for the base model?
Well, the base model's primary job is wild, real-world generalization. It needs to look at any arbitrary image from the internet and roughly understand the layout of the room or the street.
Right.
Datasets like Waymo or Megadepth provide that messy, diverse, real-world context. But the refiner, the SSR module, operates on a totally different mandate.
How so?
It is trained entirely on pixel-accurate synthetic data from datasets like Matrix City and Tartan.
Wait, if the goal is to make a model that works perfectly in the real world, why restrict the refiner strictly to synthetic data? I mean, why not use high-end LiDAR data from self-driving cars to teach it about real-world edges?
Because real-world LiDAR is surprisingly terrible at capturing fine details.
Oh, really?
Yeah. Even a high-end 64-beam Velodyne LiDAR sensor leaves massive physical gaps between its scan lines. It struggles immensely with transparent surfaces, reflective materials, and most importantly, razor-thin edges.
Oh, because the beam just misses it or scatters?
Exactly. If a laser pulse hits the very edge of a chain-link fence, the return signal is noisy and ambiguous.
Gotcha.
So if you try to teach a neural network to refine millimeter-level boundaries using noisy LiDAR data, the network just gets confused. The refiner requires absolute computational perfection.
And synthetic data provides that.
Right. Synthetic datasets generated in Unreal Engine provide clean, dense, mathematically perfect ground truth for every single pixel, which is literally the only way to supervise a network to learn these micro corrections.
That makes perfect sense. I mean, you can't teach a model to be sharper than its ground truth data.
Right.
But reading through the methodology, I immediately looked for an ablation study regarding the 3D unit, because if they went through all this trouble to gather perfect synthetic data, what if the magic is just the data?
It's a fair question.
Did they test what happens if you feed that exact same high-quality synthetic data into a massive parameter-matched 2D unit instead of the sparse 3D version?
They ran exactly that ablation experiment.
Yeah.
They built a 2D variant predicting the same log depth residuals and trained it on the identical synthetic datasets.
Okay.
The 2D variant yielded almost no improvement to the local fine detail geometry.
Wow.
It proved definitively that model capacity and high-quality data were not the bottleneck.
So the inductive bias of the 3D architecture was strictly mandatory.
Absolutely.
Because even with infinite parameters and perfect data, a 2x2 pooling operation on a 2D grid is mathematically forced to average those pixels together.
Right. The local smoothness prior cannot be overcome with scale.
The ablation study really isolates the architecture as the definitive variable for success then. No amount of compute can fix a fundamentally flawed coordinate system.
Exactly.
So the training strategy is rock solid, and the architectural ablation proves the theory. Let's look at how this actually performs against the current heavyweights of depth estimation.
Okay, let's get into the numbers.
They ran a comprehensive zero-shot evaluation across 9 diverse benchmarks, including NYUV2, KT, and ETH3D.
Right. And to really understand MoGe-3's impact, we have to look specifically at the local fine detail metrics, evaluated using a very strict 0.01 threshold.
The delta 0.01 metric.
Yeah, it's a microscopic tolerance for geometric accuracy. And under this lens, MoGe-3 vastly outperforms state-of-the-art models like Depth Pro, Unidepth V2, and Pixel Perfect Depth.
The 3D sparse refinement effectively resolves the thin structures that those 2D approaches just smear into the background.
Perfectly.
But I was looking closely at those benchmark tables, and there was one glaring anomaly that confused me.
Oh, the boundary F1 score.
Yeah. If MoGe-3 is vastly superior at resolving fine details, why does it lose on the boundary F1 metric? I mean, there's a model called Infinidepth that actually secures the top score there, beating MoGe-3 on depth discontinuity sharpness. What is going on there?
The boundary F1 anomaly exposes a massive blind spot in how the field currently measures success. Boundary F1 is strictly a 2D pixel-level metric. It simply evaluates how sharp the gradients look when projected onto the flat 2D image plane.
Oh.
And Infinidepth is explicitly optimized to produce ultra-sharp 2D boundaries.
So it's gaming the metric by drawing a really sharp line on the 2D canvas, but ignoring what that line actually represents in physical space.
Exactly. Think of it like a Hollywood movie set.
Okay.
If you view the set from the exact angle of the camera,
Yep.
the 2D perspective, it looks like a perfect, fully constructed building with sharp architectural lines.
Right.
But the moment you walk around to the back, projecting it into 3D space, you realize it's just a flat wooden facade propped up by scaffolding.
A 2D illusion.
We literally call this the 2D illusion. Infinidepth forces these incredibly sharp 2D gradients, but because it lacks a true 3D spatial understanding, projecting that depth map into a point cloud results in severe structural distortions.
Like what?
You end up with massive strings of artifact points connecting foreground objects to background environments, commonly referred to as fly points.
Oh, that is the ultimate trap for an ML engineer.
It really is.
You evaluate a model, the 2D depth map looks beautiful and crisp on your monitor, but the moment you feed that data into a robotics pipeline, your robot tries to navigate through a room filled with invisible, smeared geometric webs.
Exactly. And MoGe-3 might rank slightly behind on a 2D edge metric, but by explicitly separating occluding and occluded surfaces into distinct voxels, it maintains actual 3D structural integrity.
Which, for any practical application robotics, augmented reality, novel view synthesis 3D integrity is the only metric that actually matters.
It's the only one you can actually use.
So let's talk about the practicalities of deploying this. Scalability and inference speed are usually where iterative refinement models just fall apart.
Yeah, it can be super slow.
They tested the default VITL model, but they also scaled up to a VTG variant.
And the VTG variant pushes the local accuracy metrics even higher. It demonstrates that the SSR architecture scales beautifully as you provide it with richer semantic priors from larger foundation backbones.
But Running an iterative 3D UNet loop usually sends latency through the roof. I mean, if you're building a real-time pipeline, how slow is this?
Well, the efficiency of sparse convolutions is remarkable here. Because the network only performs math on the thin shell of occupied voxels, it skips the vast majority of the spatial volume.
Right.
So the default VITL model, running the full 3 refinement iterations, clocks in at a latency of just 121 milliseconds.
Wow, 121 milliseconds is incredibly fast.
It is.
I mean, depth anything 3 runs at around 213 milliseconds, and even depth pro is sitting at 142.
Yeah.
So MoGe-3 isn't just delivering structurally accurate 3D geometry, it is actually outperforming the current state-of-the-art 2D models on raw inference speed.
The optimization is highly impressive. And the researchers also uncovered an interesting characteristic regarding the model's stability during those iterative loops.
Oh, yeah.
The network is explicitly trained using exactly 3 iterations, k equals 3. But during inference, they push the network out to k equals 5 and even k equals 7 iterations just to see what would happen.
Normally, if you force a recurrent or iterative model to run past its training horizon, the compounding errors cause the output to completely hallucinate or, degrade into noise.
Right. But MoGe-3 showed 0 degradation.
0.
0. The evaluation metrics either stabilized completely or continued to slightly improve at k equals 7.
That's huge.
It is highly significant because it proves the model isn't just overfitting to a memorized 3-step sequence. It has actually learned a robust, physically grounded refinement process that naturally converges on the correct geometric boundary.
That is fascinating. So we have dissected the architectural mismatch, the sparse voxel implementation, the strict training curriculum, and the 2D metric illusions.
We covered a lot, yeah.
This paper really represents a monumental shift for extracting usable, structurally sound point clouds from single images.
Definitely.
But the paper concludes by highlighting a very specific limitation that I think points directly to the next major breakthrough in this field.
You are referring to the lingering issue of absolute pixel ambiguity.
Yes. Because MoGe-3 relies fundamentally on a regression-based loss function, it still struggles with uncertainty right at the subpixel boundary between surfaces.
Right.
I mean, it is drastically better than anything else, but you can still find extremely minor flight points right on the exact edge, where a single pixel technically contains half foreground and half background.
Right, because regression models are mathematically designed to average things out when faced with uncertainty.
Exactly.
If the data is ambiguous, the regression function splits the difference, which inherently pulls a few points off the surface and into the empty space between objects, creating those minor artifacts.
So here's a thought experiment to mull over as you, the listener, build out your own pipelines.
Ooh, I like this.
The researchers point out that generative models, specifically diffusion models like pixel-perfect depth, excel at resolving these ambiguous edges.
They do.
Because diffusion models sample from a learned distribution rather than averaging, they are incredibly good at hallucinating perfectly sharp boundaries.
Right.
But as we discussed with the 2D illusion, those diffusion models currently operate entirely in 2D, which creates massive structural distortions in the final point cloud.
Mm-hmm.
What if you combine these two paradigms?
Oh, wow.
Imagine a future architecture that takes the 3D sparse voxel shell of MoGe-3 to enforce strict geometric isolation, but instead of using a regression head for the log depth residuals, it runs a 3D-aware diffusion process restricted strictly to that iteratively refined sparse manifold.
That would essentially be the holy grail of depth estimation.
Right.
You'd be merging the hallucinatory, pixel-perfect edge generation capabilities of diffusion with the flawless, structurally separated 3D geometry of the SSR.
Exactly.
The sparse voxel shell acts as a physical constraint, basically preventing the diffusion model from creating structural distortions, while the diffusion process eliminates the final remaining regression artifacts.
A 3D-aware diffusion model operating on a sparse voxel manifold. I guarantee that is a paper we will be reading 6 months from now.
I'll be looking out for it.
Until then, it is time to start implementing these MoGe-3 insights into your own pipelines. Thanks for joining us, and we'll catch you on the next deep dive into the latest research on AI paper slop.
Keep building, keep refining, and stop squashing your 3D geometry onto a flat 2D plane.